Hi guys, thank you for coming to OLED Wave paper reading channel. We read the latest archived speech and NLP works. They're mostly archived papers, but today we're gonna be reviewing a very classical paper. Its title is SoundStream and End-to-End Neural Audio Codec. Why I wanna read this? Because 2 weeks ago we were reviewing the paper Audio LM, which was published about half a year ago. And I guess all of you have remembered this if have you watched our the video I recorded last time. This is the overview of the tokenizer using in the Audio LM, and the module that was being used to generate acoustic tokens is exactly something called a SoundStream. I wasn't capable of explaining the module of SoundStream in the Audio LM paper reading because we're running out of time. But today, I'm gonna dig into the SoundStream and see what its encoder is like, what is RVQ is about, and what is decoder in design like. Okay, let's go back. This is a paper which was published almost 2 years ago. It's by the people from Google, I think. All right. Correct me if I'm wrong. I think they're coming from Google, and they have shown their conclusion or result on the first page, and you can see that the purpose of this before the Audio LM was just to compress speech or something like remember the raw waveform is like a 16-bit PCM coded, something like this, linear PCM, okay? But once you want to transmit the 8 kilohertz sample speech in a telephony channel, most time you're gonna be using mu law or A law to change the, what do you call that? Convert the speech or code the speech in a certain way so you can save bits while transmitting. And before this paper, the people in this domain, the researchers in this domain, have come up with signal processing based codecs. They are EVS and Opus. I think many of us are using the Opus nowadays. I use Opus instead of OGG or AAC to give me a lower bit rate. I can store more WAV files on my hard drive. And also, I think people also come up. This EVS is developed by Google people, I think. It's a advanced. You can see it's doing better than Opus. So you wanted the bit rate as small as possible, but the Musha score as high as possible. So anything that's in this region is good, right? How to say that? You want to be close to this region. So let me draw a line, something like this. Okay. So you can definitely see that EVS is much better than the Opus. And the Lyre is a neural codec. And the SoundStream is also a neural codec, but does way better than Lyre, especially under the low bit rate scenario. Especially you can see that at 3 kilohertz BPS, it's very low, very, very low. Because think about the MP3 we're just hearing every day. Usually your MP3 file is like a 200 320 kbps. And this is 100 times smaller than your normal MP3 compression ratio, but bigger, 100 times bigger than that. But SoundStream can still achieve a Musha score around 80%. No, not 80%, about 70. It's a score from 0 to 100. You can still achieve a score above 70, which is very impressive. The reason I like this paper is this paper has had a very good introduction and detailed comparison or mentioning about the different techniques that was being used in the past audio codecs. First, they start off with the type of codecs, like I just talked about. Okay, the authors thought, okay, there are main two types of codecs in this domain. The first is a waveform codec. The other one is a parametric codec. The waveform codec, the purpose to, like they mentioned, they want to reconstruct the input audio in a faithful way. Okay. And sometimes, for example, I know the FLAC. FLAC is a lossless codec, audio codec. Lossless. So definitely it's a waveform codec, right? It would 100% recover the audio you coded before. But sometimes you can also have, for example, Opus, that is lossy codec. You can discard some of the details in the waveform and achieve a much better, much lower bit rate. Okay, so think about this. Most of any waveform codec people who have done before is all about bit allocation. Sometimes they're driven by a perceptual model, because if perceptually speaking, the speech is or the samples of speech or the features of speech is aggregated in a certain region, you wanna assign more bits to that region. So according to information theory, you're gonna achieve a lower bit rate in the end. And it's also worthwhile noting that a waveform codec doesn't make any assumption about the wave, but talking about the parametric codec, it does make assumption about what type of audio you're handling with. Especially, let's say we're trying to code in people's speech. You can just assume there is a synthesis model driven by certain type of parameters. So in that way, you can also, that's my understanding, you can just inject a perceptual model or synthesis model into the codec. So then that you can discard lots of information, because the information you injected into the codec has restricted the codec from being, or provided some information to the codec. So when you want to reconstruct the signal, you can just leverage those information you have injected into the model to give you an estimate of what the signal could be. So in this way, they can reduce the bit rate a lot. And remember the parametric, the goal is not to obtain a feasible reconstruction, sample by sample basis, but it's rather to generate audio that is perceptually similar to the original. What does that mean? For example, I say ABC, and I say ABC again. Well, the two ABC there might not be frame by frame exactly the same, but since you're my audience, you can generally tell that there's not too much difference between the two ABCs I have uttered. Is that right? ABC, ABC. They're definitely frame by frame are not the same, or even not similar. But perceptually to you, say you perceptually try to perceive the sound I said, they're similar to you. Okay. I think those things you probably, well, the authors, they do have repeated them a lot. So I would skip this part because I'm definitely going to cover this part in the following section. They talk about the related works. Here are the traditional audio codecs, aka DSP, digital signal processing. And these two algorithms they compared in a figure just above, Opus and the EVS are the DSP based or traditional audio codec. They leverage the what do you call that? LPC, linear predictive coding, CELP. I think it's a capsule excited linear predictive. MDCT. I forgot what the M is. DCT means discrete cosine transformation, I think. To deliver high coding efficiency. And then they talk about audio generative models. So it's almost 2 years from the paper was published, and then the generative model is very hot right now. Look at the GPT-3 and the ChatGPT. People are using them a lot. In the speech synthesis domain or audio generation domain, people have done also similar things. For example, the WaveNet. I remember WaveNet was published almost, when was it published? WaveNet was a sensational. I definitely recommend you to read the paper of WaveNet if you're interested in doing research in TTS or audio synthesis. I think it was published well, in 2016. This was almost like 7 years ago. It also has Dr. Alex Grave. That paper was a paradigm shift to the text-to-synthesis domain, in my personal opinion, because previously people are talking about they're not using the discriminative model, they're using generative model. It's not the generative model we're talking about today. It's more about how to get. Well, let me say this. Nowadays, generative models are indeed discriminative model, in my personal opinion, because the training process does not try to estimate the probability of py given x. X is some hidden variable, and y is the observation. That was before WaveNet. So this is a generative model, right? Generative model. But after the WaveNet, or starting from WaveNet, people start to introduce the discriminative model, or using discriminative model in the TTS, like people are doing in the ASR. Because of why? Because you only need to estimate this. I'm sorry. I have did this in the wrong direction. Guess my mind is not rolling tonight. In the generative model, all you have to do is doing this. Remember, you can think about. My mind is not rolling. What's the generative model? I've give up thinking about the name of that model. So you given an observation, what's the probability of the hidden variable? Estimating this is very difficult because it's difficult to estimate this P of X. It's very difficult. But in the discriminative model, you don't have to estimate the P of X or Px given Y. You just have to estimate this. So given an input, what's the output probability? Okay. And this is why I think nowadays, even people call GPT generatively trained. Yeah, it's generatively trained, but you should definitely classify the model into the category of discriminative model. Okay, this is WaveNet. This is after WaveNet. But WaveNet was very slow, but after that, people have tried to accelerate it, and this model has been evolved into later advanced version of itself. I think. I think nowadays people are commonly using the two type of model, these two model nowadays in the vocoder. I don't have time to explain the details of what the vocoder is, but all you can think about what the vocoder is, you can say it's the input is embedding or feature. The feature could be male scale capture coefficient, for example. Male scale capture coefficient, or some embeddings. The output is speech or voice signal. Okay. I think Melgan is faster than Hi-Fi GAN, but the Hi-Fi GAN is supposed to be generating better quality audio compared to Melgan. Okay, audio enhancement, I think is similar. This vector quantization. Author mentioned the VQVAE was also a very old paper. For those of you who are not familiar with this, I recommend you first to read the paper VAE and then read the paper VQVAE. Okay, VAE means variational autoencoder. And the main purpose of the VAE or VQ, especially the VQVAE, is this. Is try to compress the latent representation of input feature. And in this work, they propose something called a residual VQ. And also they say they're very frank. they're saying this residual VQ is a advanced version, or they developed upon the concept of VQ-VAE, which is all about compressing the latent representation of input features. Neural audio codec. They also mentioned the Lyra. I think nowadays nobody uses Lyra now. And I think if you look at this paper 40, you see interesting. So it seems to me that this paper, the SoundStream paper, is not very new, because if you look at the title of the paper 40, and they also acknowledge that it's not much different from the paper number 40. So it was published about 2 years ago. The title is Cascaded Cross-Module Residual Learning Towards Lightweight End-to-End Speech Coding. You see, that same idea is a residual learning. But me ask, what's the difference? The difference, according to the author, is bitrate scalability. So one single model can output or operate at different bit rates, while the paper number 40 cannot do that. And also the same model can also perform not only on speech but also on different type of audio signal, because it does not assume the type of audio it's working on. So it's a more like a waveform encoder other than a parametric vocal codec. What else? Yeah, let's jump to the model. So section 3 talks about the model. First of all, they talk about the encoder architecture. Let's see here. So the waveform is sampled at 24 kilohertz. It first passes through one convolutional layer, then 4 encoder blocks, then one convolutional layer, then the by-LM conditioning, then they get embedding. So the embedding is sampled with a sampling rate of 75 hertz. And you can see the K means the kernel size, the N means the number of channels, and the S means the stride size. So how do they come up with the 75? It's 24K. 24K over all the multiplication of those strides. 2 times 4 times 5 times 8, that equals 75. And in each encoder block, it's stacked by 3 residual units. I think residual units is explained on the right, and followed by a convolutional layer. And in each residual unit, the first has a dilation of 1, the second has a dilation of 3, the third has a dilation of 9. Okay. So what does the residual unit is about? It's called residual unit, right? It definitely has the ResNet connection or residual connection right here. And it's a stack of 2 convolutional layers. It's fairly straightforward. That's the encoder. For the decoder, everything is the same except the sequence going from top to bottom goes to the other way around. But they also draw the top bottom scenario style. Okay, same thing. Everything is the same. But they also compared in the experimental section, saying that what if I have a bigger encoder or a bigger decoder? To me, it's not much difference. This is a residual vector quantization. The concept is very straightforward. I think this is also the core part of this paper, the RVQ, which make this paper unique or supersede other neural codec, audio codec, and also those DSP codec. So first of all, they have a encoder output of the input waveform, right? They got a Y. Then the purpose was try to get a quantized version of Y. And the idea was just to add the output of each residual layer to the estimated Y, and also subtract that part from the residual. And you repeat this in a loop until n times or nq times to make the residual as small as possible, and also the estimated Y to be as close as the Y, original Y. Make sense? Okay. Yeah, they're talking about this is very obvious. You need the vector quantization or you'll be running out of bandwidth. Okay. Now they're talking about loss, right? We haven't talked about the loss. Where's the loss? I can't find this. Okay. Oh, loss. Okay. I think that they're training this in a GAN style. The discriminator loss is defined by this, and what is the DKT? Yeah, they're using a what do you call that? Oh, this is the adversarial loss. But this the discriminator loss is very easy to understand. This is original speech, or voice, or audio. You wanted this to be as close as to 1, but the flower G of X is generated audio. You want this to be as distant from as possible to 1, aka -1, okay? So this can be close to 0. So you want to minimize this, like I said, right? Is that clear? You want to, this is, what does the D, flower D mean? D means discriminator, okay? The purpose of discriminator is to not to identify the original speech as negative, and also identify the generated the audio as negative or -1. And then they talk about the adversarial loss for the generator or training the generator is right here, is composed by 3 parts. Let me explain each one of them one by one. The first one is very easy to understand. You want the discriminator generated the speech after passing through the discriminator to be as close as 1. I mean, it's aka for the discriminator, okay? And then this is a feature loss. This is easy to understand. The L means the or this lowercase l means the index of the internal layers. And you can see it's summed over all the L's, all the frames. The K means the discriminator ID. So they're not just one discriminator. They have in this paper they have 3 discriminators operating at the different resolutions. So this means their model is capable of running at different bit rates. Okay, they want the model to be good for at different rates, different bit rates. So K is the rate or the resolution. L is the layer. T is the frame indices. That you can see this is a L1 norm, original speech, generated speech. They want these 2 things as close as possible. The third loss are reconstruction loss in the spectrogram or spectral reconstruction loss. It's also easy to understand. I think I didn't read the details of the S, but you can definitely see that they're computing the loss in the spectrogram domain. So this is the time. Correct me if I'm wrong. My guts tells me the S means the bin indices in the spectrum, right? Definitely this is also L1 norm, but this one they're using L2 norm. I didn't have much taste into going into the details of this, so I just assume they're doing the right thing. I think in this in the next section is called the join, compression, and enhancement. They're explaining the 5-LM layer they talked about here. It's basically they're talking about, in my understanding, the model is capable of doing the 2 things at the same time, compression and enhancement. They have this parameter they can tune, so they can either, actually they're learned, not manually tuned. They can be tuned by data. So when the denoising flag is true or false, so they can operate it automatically according to the condition. Very standard. Evaluation setup, I think this is fairly straightforward. I actually didn't know much about the Musha. This is a certain type of methodology. I think it's listened by human being. They didn't use the Pascal or Poloka. They use the metrics, which doesn't have a license. It doesn't require license. It's not. Oh, I forgot to mention one thing. The discriminator architecture. Besides the generator, you have to have the discriminator, right? But it's definitely very similar to the encoder, right? You see, but the difference is they have the logics. You know what you're discriminating. Okay. I don't think you have a question about the discriminator. It's very straightforward. Very similar to the encoder, but the only thing is the output. It's supervisor training. Okay, evaluation setup. Where we were. Yeah, they compare the baseline with EVS, Opus, and Lyra, and you can see this is, I think, the first. It's almost exactly the first figure they show in the beginning of the paper, right? Anything? This is definitely better, right? But if you can see that once you got higher bit rate, the gap between the SoundStream and the EVS or Opus became smaller compared to the low bitrate case. And now you want to see the subjective evaluation result by content type. So because their algorithm claim to be working for speech, noisy speech, and music case, remember they mentioned that their model is capable of handling the noisy case, denoising, doing the denoising and the compression at the same time. You can see at the low bit rate, their 3 kbps is almost as good as EVS at 9.6 kilobits. Very impressive for almost all the scenarios. It seems to me that noisy reverberant speech is worst among all the algorithm, but music seems to be the easiest among all the scenarios. Music is the easiest. I guess it's because I think my understanding is that music contains less amount of information than the speech. Yeah, medium bit rate is, you can see SoundStream is better than Opus at 6 kilobit, 6 bps, while Opus is operating at 16 kbps. While the high bit rate case, I think everybody is doing fairly okay, especially when the bit rate is high, I think. But SoundStream is still doing way better than others. I think those are the following are fairly details. It's very useful if you want to implement the SoundStream by yourself, and you can just play with the encoder, decoder, and the other configurations to see whether your result match their reported results. I guess I will stop here. How do you think about the video? If you like us or our video, please hit subscribe and share that video with your friends. Well, I will see you next week. Bye.